Hi everyone, welcome to the lecture 5 in this course, Classical Mechanics 1. So today in lecture 5 we'll discuss we'll continue with the constraints, and then we'll introduce generalized coordinate, configuration space, etc. But before we begin today's lecture, let me review or recap what we have learned in previous lectures. So recap. Okay. So in lecture 1, as you remember, we just introduced this course. So it was introduction. In introduction we discuss about the course content, we discuss about the study material, books, we discuss about the plan, etc. Then in lecture 2 we discuss about the Newtonian mechanics. So in very briefly we only mention about Newton's laws of motion and how to calculate a classical system. A classical system means you have to find the position of the system. System means consists of one particle or many particle. So each and every particle's position for all time you have to find. So you find that by solving second order differential equation as given by Newton's second law. Then in lecture 3 we continue with the Newton's mechanics and find the difficulties or disadvantage or problems in Newtonian mechanics. Then in last lecture we discuss how this can be overcome and need of new formulation. Lecture 4, new formulation. So we discuss constraints, and degrees of freedom. So we discuss the degrees of freedom of a classical system, and when we have constraints, degrees of freedom will be less. So we discuss various type of constant. We discuss how degrees of freedom can be calculated in last lecture. So let us start today's lecture with the review of the constant, which are very important. So constraints means the restriction. Let me repeat again. Constraints mean the restriction to the motion. Okay. So restriction to the motion. So for example, I said the particles moves in a plane. So a plane can be described by a two-dimensional plane is two-dimensional and can be described by two coordinates x and y. But if we put additional condition that particles moves on a circle, so this is the constraint equation. So this is constant equation, and this will reduce the degrees of freedom, as we defined in last class, that it is the number of independent then variable to specify the system. The position position of the system at particular time. This is important. So, particular time. So, in a particular time we need how many variables, that will give you the degrees of freedom. So, now degrees of freedom will be less when you have constraint in the system. Okay. So, in this case when particle is supposed to move on a plane, degrees of freedom is supposed to be 2, that is the maximum possible degrees of freedom for a single particle, and there is one independent constant. So, degrees of freedom will be less. So, this all these things we discussed in the last class. Now, there are various type of constraints. So, we discussed. So, let me quickly go through this again. So, different classification. So, we discuss at least 3 different classification. First one is holonomic and non-holonomic. So, so the constants either can be holonomic or non-holonomic. So, what are the holonomic constant? If the constant equation you can express in terms of equality like this, then it is called holonomic constant. So, 2 important characteristic: one, does not depend on velocity, so no velocity dependence. And it equal sign. So, no velocity dependent and equal sign. So, the constant I just mentioned, the particle moves on a circle, you can express an x square plus y square equal to a square. This is with the equal sign and no velocity dependence. So, it is a holonomic constant. On the other hand, all other constants are non-holonomic. Those who are not holonomic are non-holonomic. That means you can have a velocity dependence, non-trivial velocity dependent. Non-trivial velocity dependence means you cannot integrate that velocity to find a velocity independent equation. So, we have seen some example, and if the particle is constant in such a way that you cannot write a equal sign. For example, if particle are confined to a spherical container or some box, so the r should be less than equal to the radius of the spherical container. So in that case no equal sign, so such constants are non-holonomic. Similarly, if a sphere rolls over an inclined plane, then you will able to see that in the condition that it's rolling without slipping, that v equal to omega cross r. So in that case it's velocity dependent. So if you cannot eliminate all these velocities, then it is a non-holonomic constant. So there are many examples in both holonomic and non-holonomic constant. In this course we mostly confine ourselves to the holonomic constants. Then the next type of classification we have, depending on the time dependence in the constant equation, we defined in 2 categories. So this is completely different categories, this different classification. So all constant either holonomic or non-holonomic over. Now again different type of classification is geonomic and scleronomic. So geonomic, this explicit time dependence, and there is no time dependence. Okay. So here also we provide certain examples. For example, if you have a pendulum, with this fixed length, then the constraint for the pendulum will be scleronomic, because it does not, length does not change with time. But if we put some special pendulum where the length of the pendulum is time dependent, it depends time on explicitly that its length changes with time, then such constraint will be duonomic. So this is another type of classification. Then next we consider another category which is known as, so third classification was conservative and non-conservative. So I hope you all are familiar with the conservative force and non-conservative force. So if the force behind the constraint is conservative type, then it is called conservative constraint. The force which causes the constraint is non-conservative type, then it is called non-conservative. So all the constraint is caused by some force. So constraint force is conservative, and in the non-conservative constraint, the constraint force non-conservative. And we'll, in tutorial class we will see that the constraint in the rigid body. So what is a rigid body? That I mentioned in the last class also. Rigid body is a collection of point particles, or particles which we mean point particles, collection of particles with fixed interparticle distance. That means distance between any two particles is constant. So if such happens, then that collection of particles is called rigid body, and we will see in tutorial class that the constraints in a rigid body conservative type. Okay. So this is the review of last class, and now we will go to the today's class, and we will see that concept of generalized coordinates. So before that let me point out again, I mentioned that constraints creates two type of problem in the classical mechanics or in the analysis. So constraints put two problems or create two problems. First one is that all variables are not independent. All variables are not independent. So one has to be careful. Some of the variables are dependent, some of them are not. For example, if you have a motion in two-dimensional, so in two-dimensional motion, and we said that constant is x square plus y square equal to a square, then both x and y cannot be independent. So either x is independent or y is independent, one of them will be independent. So when constant is present, all variables are not independent. So this is the first problem arises due to the presence of constant. Second one, the force of constant constraints are not furnished a priori. are not furnished a priori. You don't know the nature of the force beforehand, and to deal with such a situation is much more difficult. So now I am going to propose that in case of holonomic constants, the first problem, that all variables are not independent, we can address the first problem by proposing generalized coordinate. So the first problem for holonomic case, holonomic system can be addressed by generalized coordinate. So we will learn what is generalized coordinate. So first problem is that all variables are not independent. So suppose I study a two-dimensional system, again a two-dimensional system. So we expect that all dynamical variables are function of two variables x and y. Now I said that the particles moves in a circle. So constant equation will be x square plus y square plus a square. Now I said that all dynamical variables are function of x and y, but subject to this condition, constant condition. So constant equation x square plus y square. That means all two variable x and y are not independent, okay, but this is a holonomic constant. We have a equal sign and we can replace, say for example x, I can write plus minus a square minus y square, and I replace in the dynamical variables all x by this expression plus minus a square minus y square. So now all variables, all dynamical variables or physical quantities will be function of y only, and this is independent. So I have one variable and that variable y is independent now. So this way one can get rid of the constant, one can find that number of independent variables. Alternatively this problem can be solved Alternatively, if I write x equal to a sin theta and y equal to a cos theta, then I substitute all dynamical variables and will find that will be theta only will be independent variables. So I reduce the problem to the independent variables and now we can carry on our. So the first type of problem that all variables are not independent can be handled by proposing generalized coordinate. Okay. So let us define what is generalized coordinate. So generalized coordinate as defined, that S independent variables generally denoted by Q's, Q1 to Qs, which completely specify the position of a system with S degrees of freedom are called generalized coordinate. So let me repeat. So S independent variables generally denoted by Q, so Q1, Q2, Q2S, which completely specify the position of a system with S degrees of freedom. So for if the system has S degrees of freedom, you need S number of variables independent to specify the position of a system, of that system, are called the generalized coordinate. They can be anything. They can be the Cartesian coordinate, may or may not be Cartesian coordinate. They may be anything. So there is no, they may be scalar, they may not be the Cartesian coordinate, they may have any dimension. So these generally, these variables may have any dimension so it can be dimension of length, it can be dimensionless, it can be any other dimension, and these will not be restricted to a particular coordinate system. Okay. So this is the generalized coordinate. So again, let us consider few examples. So if I consider three-dimensional 3D space and with the constraint that particle moves on a surface of a sphere. So this is the equation, constant equation, because particle moves in a surface of a sphere. So you can constant equation you can write like this, and one can show that spherical polar coordinate, if you use x equal to a sine theta cos phi and y equal to a sine theta sine phi and z equal to a cos theta, which will satisfy this condition, which will satisfy this x square plus y square plus z square equal to a square condition. So you can find that the any dynamical variables for this system, it will be function. So any physical quantity or dynamical variables will be function of theta and phi. So in this case, so in this example, the generalized coordinates are theta and phi. So theta and phi are generalized coordinates. Okay. In this context, I want to mention that there are many ways, there may be many ways to find generalized coordinates, but one has to be careful of the generalized coordinate which will be helpful for calculation. For example, in this case you can eliminate z and write your dynamical variables only are x and y. through this equation. So you can eliminate your z through this equation, and you can claim that your x and y are generalized coordinate. So for example, x and y, by eliminating z, if we eliminate z, then you will have only two independent variables x and y, so they can be also generalized coordinate. Okay. Now there will be a, okay, at this point let me ask few activity questions. So let me ask how many generalized coordinates? So first question is how many are required for, so I'll give you two system for a spherical pendulum, say spherical pendulum, the double pendulum, see a 2 mass 3 spring system in one dimension for a rigid body okay. So this is the activity question. So you try to think of it, that how many generalized coordinates will be there. Also you find what are the constraint equation, and then what how many variables you need and what will be the choice of these variables. Okay. There will be a concept of quasi generalized coordinate which will explain with the examples. So when we have a non-holonomic constraint, then also your degrees of freedom will be reduced, but since non-holonomic constant cannot eliminate the coordinates, so you still need a generalized coordinate for the non-holonomic constraints. Those additional generalized coordinates are known as quasi generalized coordinates. So this will in the tutorial class will consider example to clarify this issue more. So before I finish this lecture, I'll define what is the meaning of configuration space. So next class will be tutorial class, and in the tutorial class this will consider some example to illustrate the concept of quasi generalized coordinate. So we'll consider some example where quasi generalized coordinate is present. So the space spanned by the configuration space is the space spanned by the generalized coordinates. Space spanned by the generalized coordinates. That means all the suppose you have a system with 5 generalized coordinate. Okay. So this 5 generalized coordinate can consider as a mutually perpendicular direction, and if you can imagine such space, so that space is called configuration space. So this is the configuration space for this 5-dimensional system, or system having 5 generalized coordinate. So configuration space is 5-dimensional in this case. And important point statement about the generalized coordinate, configuration space and generalized coordinate is that every point in the configuration space represents system at particular time. Okay. So with this I will stop this class, and in next class will be the tutorial class. So if you have any queries, questions, please put in the discussion forum and we will answer this. Thank you.